Hello everyone, I'm Fawzul Atiq. I'm giving some series of lecture on the course Probability and Statistics. In the previous lecture, we have discussed about the independent event. Even before that, we discussed conditional probability, right? Several things we have already discussed. So in the today's lecture, we'll discuss about the Bayes theorem, which is again related to the conditional probability. Let us see what is the Bayes theorem. We know that for any two event, the multiplication rule says what? For any two event E and F, we know that it is P of E intersection F equal to P of E given F into P of F. This is again came from the conditional probability definition only, right? Now, on the other hand, we know that P of F given E is what? That is the conditional probability of F given E has already occurred. It is P of E intersection F divided by P of E. And then you apply the above formula, substitute this value to here, and we can get P of E given F into P of F divided by P of E. Right? Very easy to get that formula. This formula, we called it as Bayes theorem. Sometimes you called it as Bayes formula or Bayes rule, right? So with how we get it, it's very easy to get. It's conditional probability definition and multiplication rule. Both will together gives you the Bayes theorem, right? So therefore, we have this formula P of F given E equal to P of E given F into P of F divided by P of E. See, it is like when you have to apply the Bayes theorem, when you have two individual event E and F, right? And they are depending on each other. So probability of occurrence of E given that F has already occurred, these are all depends, right? So one of the things is already given. You know their individual probability E and F, probability of E and probability of F you know. Now it is you also know that probability of E given F is given. So one of the event, occurrence of one of the event given that another event happened, then you can get the other side, that P of F given E, right? So you have two individual event E and F whose probability you know, P of E, P of F, and P of E given F is also you know. So if you know such thing, you can able to get the other side, P of F given E, with the help of Bayes theorem. Correct? We'll do one example so that it will be very clear when you have to apply the Bayes theorem. Now look at this problem. 1% of people have a certain genetic defect, right? 90% of test for the gene detect the defect, true positive. So 90% test will get it that okay, the person have the genetic defect and it will detect that it is a positive one. And irrespective of the defect, 10.4% of tests show positive. Now this is like the test which used to get that okay, whether the defect have it or not, that has some issue, that whether the person have the defect or not, it says 10.4% always show it is a positive one. So irrespective of the defect, it will always show you it's a positive one. Now, if a person get a positive test result, what is the probability that they actually have the genetic defect? Now, somebody already got a positive result in that test. Now, in this case, why these questions are arising? That is, what is the probability that they actually have the genetic defect? Because of this line, that 10, irrespective of the defect, 10.4% always show positive. That means the person, although the test show it is a positive one, but still there is a chance that it may not be that actual problem, because irrespective of the defect, 10.4% test always show positive, right? So you have to get what is that probability that they actually have the genetic defect, correct? So you see, uh, let us denote some event with some letter. Let D denote the event that a person has the genetic defect, and T denote the event that the test shows positive. Then let us see what are the things are given. 1% of people have a certain genetic defect. What does it mean? It means that P of D, it is 1 by 100, which is 0.01. Now 90% of tests for the gene detect the defect. It means that some person have already have the genetic defect and the test is showing positive. So what is that probability? 90%. So probability of getting a positive test given that the person already have the genetic. So it means what? P of that positive report given that already. So P of T given T. And it is 90%. So it is 0.9. 9 by 100. So 0.9. And what is given? Irrespective of the defect, 10.4% of the test show positive. That means this is the that T will always like have the showing positiveness. It is 10.4% are there, whether the person have that defect or not. It, right? So it is basically P of T, and which is 10.4%. So this 10.4 divided by 100 will give you 0.104. Now what you have to find from this question, if a person get a positive result, what is the probability that they actually have the genetic defect? That means if a person gets a positive result, so this is the given one, what is the probability that they actually have the genetic defect? So you have to find out P of D given T, right? Now see, you have already in your hand D and T are two events. Probability of D is given, probability of T is given. Now probability of T given D is also given. You have to find probability of D given T. How you can do? Yes, we have to apply the Bayes theorem, right? And by applying Bayes theorem, we can get P of D given T is equal to P of T given D into P of D divided by P of T. Now just apply the substitute all this value. It is 0.9 into P of T is 0.01 divided by P of T is equal to 0.104. And if you calculate, you'll be getting the value is 0.0865. So if a person gets a positive result, what is the probability that they actually have the genetic defect? It is 0.0865. Clear? Okay. So yes, this is the answer. We have already discussed this one. Okay. Now the law of total probability. What is that? Let F1, F2, Fn be the mutually exclusive and exhaustive events. F1, F2, Fn are mutually. Now, mutually exclusive means all of us know F1, F2, Fn, all of them are mutually exclusive. That means what? None of them have any common outcomes. So all are disjoints, right? So Fi intersection Fj equal to 5. So each of the F1 intersection F2 is equal to 5. F1 intersection F3 is equal to 5. Fi, F2 intersection Fn all are 5. So Each of them pairwise, if you take their intersection, they are disjoint. That is, you call it as mutually exclusive. And they are mutually exhaustive also. What do you mean by exhaustive? If you have that all of them together, if you take their union, it, you would give it that is the whole sample space S. If you have such case, you call them, they are the mutually exhaustive, right? So basically you have this, suppose this is the sample space, and you have some event like this F1, F2, maybe F3, or somewhere here it's a big event F4, like this. You have the event. So this is F1, F2, F3, F4, F5, F6, which you can see that none of them have any common outcomes, and all of them together, all of their union gives you the whole sample space S. So these events F1, F2 up to F6, all of them are mutually exclusive and exhaustive events. Now, suppose you have any another event, maybe an event E is there, any general event in the sample space, and suppose this is the any event E. Possible. So the red color one is the event E. Then we can also see that this event E you can write down in this form. So this is the E is intersection, E intersection F1 is this part, E intersection F2 is this part, E intersection F6 is this part, E intersection F5 is this part, E intersection F4 is this part, and E intersection F3 is this big part. Correct? So E is basically it is the, so in general, if I just write theoretically also, we can easily see this. We can easily see that what is E. So we know that for any event E, E is equal to E intersection S. That means E is equal to E intersection S. S is the sample space, universal set. So S can be written as union of this events. So I'll just write down that one, F1 intersection, it's a F1 union, F1 union F2 union dot 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 to Fn. And then I can easily write down that E intersection F1 by the distributive law, E intersection F2 union dot 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 up to union E intersection Fn. This is by the distributive law of sets. And we also have seen that this part E intersection F1, this is somewhere here. E intersection F1 is there, this place. E intersection F2 is this place. E intersection F3 is this big place, right? And similarly, we can see that all of them are mutually exclusive. They do not share any common outcome. Therefore, what we got is all of them, this one is mutually exclusive with this one. So all of them are mutually exclusive. The event E intersection F1 intersection Fn. Now, if we have such case, because all of them are mutually exclusive, I can write down the probability of E equal to the probability of union of all this event, probability of union of all this event. And we know that axioms of probability, that if you have individual probability and all of them are mutually exclusive, then it is the probability of their individual sums. So it is equal to summation of I equal to 1 to n P of E given intersection Fi. And for each of the individual event, we know from the multiplication rule, I equal to 1 to n, I can see that P of E given Fi into P of Fi. Right? So this is called the law of total probability. Now look at that. We have derived this one. law of total probability. So if F1, F2, Fn are mutually exclusive, so if you have a sample space which is exhausted by the some n number of mutually exclusive event, then for any event E, you can find its probability in with the help of this law of total probability method. Clear? So let me move to give you an example. Actually, before that, before going for an example, if I have any particular event A, it is given and another event E we have. I'm trying to apply this law of total probability with the help of this event A. Now we can write that the sample space A is equal to A union A complement. I can write. Now A union A complement, what kind of event they are? They are mutually exclusive and also they exhaust the sample space. So this one and this one are mutually exclusive. Their union is the sample space. So we can apply the law of total probability here. So if I apply this, I'll get probability of any event E is equal to P of E intersection A plus P of E intersection A complement, and which is given by P of E given A into P of A plus P of E given A complement into P of A complement. Right? So the law of total probability we can also apply that if I have just two events. So for any event we can find its probability with the help of another event by taking A and A complement as mutually exclusive event and mutually exhaustive event as clear. So therefore we have this one that for any two event A and E, the law of total probability can be written as P of E equal to P of E given A into P of A plus P of E given A complement into P of A. Now why this method is very useful, I'll show you an example. Look at this one. Read this question. You ask your neighbor to water a sickly plant while you are on vacation. So you'll go for a vacation. You ask your neighbor that please give some water in this plant, which is little bit sick. Now without water, it will die with probability 0.8. With water, it will die with probability 0.15. And you are 90% certain that your neighbor will remember to water the plant. See, all these things depends on the conditional probability, right? Without water, it will die with probability 0.8. That means what? Probability of the event that it will die given that it did not get any water. With water, it will die with probability 0.5. That means what? Probability of it will die given that it got some water. Now this one, you are 90% certain that your neighbor will remember to water the plant. So this is the individual probability, that probability of the event that the plant will get some water, it is 90%. You have to find that what is the probability that the plant will be alive when you return. You have to find the probability that the plant will be alive when you return. And next is, if it is dead, what is the probability that your neighbor forgot to water it? So we'll first think about the first one. Now let us denote the events by some name. Let A be the event that the plant is alive after your return. And let W be the event that the plant received water during the vacation. So now A is an event whose probability depend on whether it will get some water or not, right? So some event we can create which is the event W, and W complement will makes you the whole sample space. A is another event that the plant is alive after your return. So we have to get the probability of the event A with the help of the event W, right? So how we can do it? Think of it little bit, all of you. So few of the things are already given here. Okay, let us understand what are the things are given. Without water, it will die with probability 0.8. That means probability of it will die with probability 0. Die means opposite of the event A, complement of the event A. So P of A complement. Given that without water, P of A complement given W complement, which is 0.8. With water, it will die with probability 0.15. What does it mean? So P of A complement, it will die given that it will get some water. It is 0.15. You are 90% certain that your neighbor will remember to water the plant. That means it is the event that the plant receives some water during the vacation, right? So it is P of W. And it is given that 90%, so it is 0.9. Right? You have to get the probability of the event A. So P of A you have to find out. Now this is the law of total probability we can use now. So you have this whole sample space. It is divided by, exhausted by two events, W and W complement. You have another event A, which is like that. So it has some intersection with W, it has some intersection with W complement. We can apply the law of total probability. What it says? It is equal to P of A given W into P of W plus P of A given W complement into P of W complement. Law of total probability. Clear? Now we can get all this individual thing because it are already given. So what is P of A given W? P of A given W. So it is 1 minus P of A complement given W. How I got this result? This is the conditional probability properties, because we know that for any condition, whatever property satisfy for ordinary probability, they will also satisfy for the case of conditional probability, right? So the given W is the event which is already given. Then probability of A is equal to 1 minus P of A complement. So we apply that theorem, and therefore this value is equal to, because this is already we have, so 1 minus 0.15, it is 0.85. Similarly, P of W I already have. P of A given W complement. We have to find this part. A given W complement, in the same way I can write P of A 1 minus P of A complement given W complement. So it is A complement given W complement is 0.8, so therefore it is 0.2. And at the same way, we can get P of W complement is what? Because I need this one also. It is 1 minus P of W. It is 0.1. So we got all this thing. We can substitute these values in this part. And if I just substitute it, I'll be getting these values are just, if I substitute, I'll be getting this thing. Maybe I'll do it here somewhere. So this value is equal to, I'll change the color. So this is P of A given W is 0.85, sorry. 0.85 into P of W, it is 0.9 plus P of A given W, we already W complement is 0.2 into P of W complement, it is 0.1. So if I just substitute all the value, If I just, and then if I do the simplification, we'll be getting 0.785, right? So this is the probability that the plant will alive when you return. Clear? So we got the P of A. Now look at the next question. If it is dead, so the next question is, if it is dead, what is the probability that your neighbor forget to water it? That means what? If it is dead means what? It is A complement. What is the probability that your neighbor forget to water it? That means what? That the plant did not get any water. So it is the event W complement. So you have to find the probability of the event W given that A complement. You have to find the probability of the event W complement given that A complement already happened. So for this, you have to find that P of W complement given A complement. Now P of W complement given A complement, how we can find? What are the things we have already in our hand? P of A complement given W complement. We already have this. P of W complement also I have, right? From this I can already have P of W complement. So I have to get the other one. So how we can do this? Yes, Bayes theorem. So if I just apply the Bayes theorem, I will be getting P of W complement given A complement is equal to P of A complement given W complement into P of W complement divided by P of A complement. Now all this value we already have it. P of W complement we already calculated. It was 0.1. A complement by A complement given W complement it was 0.8. Maybe I'll write in that side. So this value is 0.8. So this is the value of 0. W complement. This is the value of P of A complement given W complement divided by P of A complement. But P of A we already calculated. So it is 1 minus 0.785. If you simplify it, you'll be getting this value 0.372. So this is the probability that your neighbor forgot to water the plant given that it is dead. Clear? Okay. So you can just have a look into it. The answer, whole answer, it is already given in this form. So all these things are here. Okay. Let me just discuss the last one topic called generalized Bayes theorem. So this is the Bayes theorem. We can get these things with the help of Bayes theorem only. So how we can do? Suppose that F1, F2, Fn are mutually exclusive event and they are exhaustive as well. Mutually exclusive means they are individually, all of them have the disjoint event, and exhaustive means their union is equal to the sample space. If you have such case, then for any event E, we can have P of Fj given E is equal to P of, that is from the conditional probability definition. And then we can just apply the multiplication rule in the numerator. It is P of E given Fj into P of Fj divided by, we know the law of total probability, that E is equal to sum of this event. So I can have, this is the summation of I equal to 1 to n P of E given Fj divided by P of Fj. So this is called the generalized Bayes theorem. Sometime you can see that this theorem is again very, very helpful. Correct? Let us have an example. Look at this. Suppose that we have three cards that are identical in form, except that both sides of the first card are colored red, both sides of the second card are colored black, And one side of the third card is colored red and other side colored black. So there are three identical shape card I have. One card is both side red, another card is both side black, and the third one is one side black, one side red. Now, these three cards are mixed up in a hat and one card is randomly selected and put down on the ground. So all these three cards, we kept it in a hat and it is just mixed up, and you picked one card from this hat and keep it in the floor, in the ground. Now, if the upper side of the chosen card is colored red, what is the probability that the other side is colored black? You have to find this probability. Now, these things can happen in many ways. The upper side of the chosen card is colored red. What is the probability that the other side is colored black? How to do that? So, for that, first let us denote this event. Let RR, BB, and RB denote those cards respectively that the chosen card is all red, all black. So this is the card that both side it is red. This is the event the chosen card is both side red. This is the event both side is black. And this is that mixed up card that one side is red, one side is black. And further, let R be the event that the upturned side of the chosen card is red. What you have to find here by looking at the question, if the upper side of the chosen card is red, what is the probability that the other side is colored black? So it is the probability of this event given that it is the chosen card, upper side of the chosen card is colored red. So when it is possible, it is for the red black card only. So red black card you have to get given that the like red color already happened. So you have to find the probability of the event other side color is black. So probability of the you have to find probability of this colored red black card you have to get basically given that R is already happened. So whenever R is already happened, red colored one upturned face. So when you can get the probability of the other side is black, which card it is? That means you have to get the RB card now. So this probability you have to find out. How we can find? We can apply the generalized Bayes theorem. So we have actually three mutually exclusive events that RR, BB, and RB. And R is one event which depends on them. So it is P of R given RB into P of RB divided by, just we are applying the generalized Bayes theorem. It is P of R given RB into P of RB plus P of R given the BB into P of BB plus P of R given RR into P of RR. Now we can able to create that, find all this probability individually. So what is this probability P of R given RB? What does it mean? So probability of the upturned face is red given that that card is a RB card. That means one side red, one side black. So you already have got the one side black, one side red card. Then what is the probability that it will get the R side, red side? Yes, it should be 1 by 2 because you have only two choices. So it is 1 by 2. What is the probability of getting this RB card that you will select this? You have three cards. What is the probability of getting one card? It is 1 by 3. So the first part is done. Now what is this probability? Probability of R given BB. So you have chosen. So given that you have already selected the both side black card. What is the probability that the upturned face is red? Is it possible? You have already got the black, both side black card. So it is never possible. So this probability is 0. And this one, although I don't need, but probability of BB it is 1 by 3 getting this card. Now what about this one? Probability of R given RR. So you have selected the both side red card. Then what is the probability that whenever you are putting it in the ground, what is the probability that you will get the upturned face is red? Now both side it was red. It will bound to happen. So this probability is always 1. And in the same way, P of R is selecting this card is 1 by 3. So if you substitute all this value, you will be getting, maybe I'll do it in the red color. You just substitute all this value. So this probability is given by 1 by 2 into 1 by 3 divided by, again, 1 by 2 into 1 by 3 plus 0 into 1 by 3 and plus 1 into 1 by 3. So if you simplify it, you'll be getting this answer is 1 by 3. Thus the probability that the other side of the card is black, it is 1 by 3. Clear? So these are the some examples. So this is the whole proof. As we already discussed, this is the question, the answer. Yeah, that's what we have discussed. So all the questions and content, mostly I have taken from these references. So if you have liked the video, please give your feedback. I hope that these videos are helpful for you. We'll meet in the next video. Thank you very much.